Our next topic is areas of polygons and circles. So let's start with a definition of area. Area is the amount of space inside a flat, two-dimensional object. Now keep in mind that we've just talked about what length is. Length is just a one-dimensional measure. But when we talk about area, we're looking at a way to measure the size of a two-dimensional object, a way to measure the amount of space within that object. So in this case, if we have a rectangle that measures 3 inches by 2 inches, we can think of dividing the rectangle up into units that are 1 square unit each. And in that case, we would have 6 square units inside this rectangle. So if we're trying to find the area of a polygon, what we're really looking at is how many square units can we fit inside the shape. And for a rectangle, finding that's fairly simple. If we know the length of the base of the rectangle and the height of the rectangle, all we have to do is multiply the base times the height. You may remember that area formula as length times width, and that certainly works as well. In this case, the base of the triangle measures 3 units long and the height measures 2 units, so the area is 6 square units. And you can see we can fit 6 squares inside the rectangle that are each 1 unit by 1 unit. Now triangles get a little bit trickier, because if we try to fit those squares inside the triangle, we find that we don't necessarily have complete squares to count. So there is a way to find the area of a triangle that involves taking this triangle and duplicating it. So let's say we have an exact copy of this triangle. The two triangles have exactly the same area. And we're going to take the purple triangle and fit it right next to the blue triangle. Now you can see that we've created a rectangle, and it's easy to find the area of that rectangle. It's just the base times the height. But the area of the rectangle isn't the same as the area of the blue triangle we started with. In fact, the blue triangle is half of that area. But that leads us to a formula we can use for the area of a triangle, which is area equals 1/2 times the base times the height. Now what's really important to notice is that the base and the height of a triangle will always be at right angles to each other. In this case, we have a right triangle, so that's fairly easy to see. The area of this triangle is 1/2 times 3 times 2, which is 3 square units. Now you won't always have right triangles that you're trying to find the area of, but you can always name something that you're going to call the base and something that you're going to call the height of your triangle. Remember, the base and the height will always be at right angles to each other. Now imagine that we take a second triangle and lay it right on top of that blue triangle we were trying to find the area of. We now have 2 triangles, not 1. But if we take that top triangle and we cut it and rotate the pieces, we've once again got a rectangle. And that rectangle has an area that's equal to its base times its height. But the blue triangle, which is the one we want to find the area of, is half of that area. After all, it took 2 triangles to make this rectangle. So one triangle has an area that's half of the area of the rectangle. So once again, we have that the area of the triangle is 1/2 times the base times the height. Now how about if we have a parallelogram? Once again, we can identify a base and a height for a parallelogram. And once again, if we try to take this parallelogram and divide it up into square units, we have some whole squares we can count, and we have some partial squares. So how can we decide how many whole squares we have inside this parallelogram? Well, here's what we're going to do. Let's take the parallelogram and let's cut it right along the height and simply move that triangle on the end to the left side. We've got exactly the same area, but now we have a shape that we can identify. We have a rectangle, and the area of that rectangle is the base times the height. So the area of this parallelogram is exactly the same as that. It's the base times the height. So the area formula we have for a parallelogram is identical to the area formula for a rectangle. It's important to notice that the base and the height are always going to be perpendicular to each other. In this case, we have a parallelogram that has a base that measures 3 units and a height that measures 2 units, so the area of this parallelogram is 6 square units. Well, what could we do with a trapezoid? Well, let's imagine that we have a trapezoid that has 2 parallel bases that are different lengths. So we'll call the longer base base 1 and the shorter base's length base 2. Now it also has a height, and the height of a trapezoid is always going to be perpendicular to both of those parallel bases. Obviously, we have some perfect square units inside this trapezoid and some partial square units. So how can we figure out how many square units of area we have in the trapezoid? Well, let's imagine we lay a second trapezoid right on top of the first one. So we have an orange trapezoid laying right on top of the blue trapezoid. And now we're going to take that orange trapezoid and just move it until it fits right there. Now remember, the orange trapezoid was exactly the same size as the blue one that we're trying to find the area of. So it has lengths of its bases that are also called base 1 and base 2. And if you look at the entire figure we've now created a parallelogram, and we know how to find the area of a parallelogram. That's simply base times height. Now here's the tricky part. What's the base of the parallelogram measure? Well, the base of the parallelogram is base 1 plus base 2. So the area of the parallelogram is base 1 plus base 2 times the height. Now that's all fine and well, but we just want the area of the blue trapezoid. And the blue trapezoid is half of this picture. So the area of a trapezoid is 1/2 times the sum of the bases times the height. And in this case, the two bases measure 4 units and 2 units, and the height is 2 units. So the area of this trapezoid is 6 square units. Now circles are trickier yet, because remember, we're trying to fit a number of square units inside a circle. So to find the area of a circle, we're going to use an area formula, which is that the area of a circle is pi times the square of its radius. We're still going to say that if we want a decimal approximation for that area, that we can substitute 3.14 for pi. If we want an exact answer for area, we're going to leave pi in the answer. So what if we have a circle that has a 3-inch radius? How can we find its area? Well, we know that area is pi times radius squared. So the area would be pi times 3 squared, which would be 9 pi square inches. And if we substitute 3.14 for pi, we get an approximation of 28.26 square inches of area inside the circle. Now we've talked about arc length as it relates to circumference of a circle, that arc length is a portion of a circumference of a circle. Well, we have something that compares to that with area, and that's called sector. A sector is a portion of a circle's area. So if we wanted to find the area of an entire circle, we certainly could. We could find the area of this circle if we knew its radius, and we do, it's 12 feet. But what if we want to find the area of a sector of a circle, a 60-degree sector? That means we're looking for the area of that pie-shaped piece of the circle. Well, all we need to do is find the area of the entire circle and then figure out what fraction of the circle that 60-degree sector is. So the area of a circle is still pi r squared, and the fraction of this circle is 60 degrees out of the 360 degrees that take up the whole circle. So the area of this circle is 24 pi square feet. Now there's something that's often used in schools to allow students to explore area, and that's called geoboards. So we're going to take a look at a virtual geoboard first so you can see what they're like, and then we'll look at some areas with geoboards. So this virtual geoboard is from the publisher Glencoe. What you see is some pegs, and you see some different colored rubber bands over on the left. So when students are using geoboards, what they do is they take rubber bands and they put them over the pegs, and then they move the rubber bands around the pegs in order to make geometric shapes. So for example, if I wanted to look at the area of a triangle, I could stretch the rubber bands over the pegs to make a triangle that in this case has a base that measures 3 units and a height that measures 2 units. So its area would be 1/2 times 3 times 2, or 3 square units. Or maybe I want to find the area of this rectangle. So I could say that the area is, let's see, base times height would be 3 times 2. So the area of this rectangle would be 6 square units. So I can make lots of different shapes on these geoboards with the rubber bands and determine the area of the shape simply by looking at either the dimensions of the shape that I have, or I could just count the number of square units inside the shape. If I have, let's say, something like a square, I could certainly add the number of square units inside, so I can count 4 square units, or I could say, well, this is really a rectangle, so let's just multiply its base times its height. 2 times 2 is still 4 square units. So geoboards are very instructional for students to use, and we're going to look at some shapes on geoboards and see if we can find the area of each of those shapes. So you can see lots of designs here that are made on geoboards. Certainly none of them fit the shapes that we've looked at, the triangles or the rectangles or the parallelograms, but we can find the area of all of these shapes that you see. So let's just take a look at a few of these. There's basically 2 methods that we can use for finding the shape of an irregular figure like this. And one is to break the figure up into smaller pieces that we do know how to find the area of. And there's more than one way to do that. We might do something like this. There's a rectangle on the right side of that line we just drew, and if we drew a couple more lines, I can see some triangles and a square, and they're all familiar shapes. They're shapes that we know how to find the area of. So now let's just do that. Let's find the area of each of these individual little shapes. That triangle is half of a square unit. That square is 1 square unit. The rectangle is 8 square units. That triangle is 1 square unit. And this one is also 1 square unit. So the area of the original figure is the sum of all of those areas, which is 11.5 square units. Now we could do that same method on this particular shape, but let's look at a different method that sometimes is useful as well. Sometimes we can find the area of a figure by doing some subtraction. In other words, look at that figure as being contained within a rectangle. So if we can find the area of the rectangle that we just drew, and then subtract the area of those triangles that are in the rectangle surrounding that red figure, we'll have what remains, which is the area of the red figure. So the yellow triangle we just drew is 3 units by 4 units, so its area is 12 square units. But now we have to subtract off of that the area of the 4 triangles that surround the red figure. So this one is 1 square unit in area. That one is 1.5 square units in area. This one is 1 square unit, and that one is 2 square units. So we need to subtract off the areas outside of the red figure. And when we do that, we end up with 6.5 square units. So the area of the red quadrilateral is 6.5 square units. Now this idea of subtracting area can be useful in other ways that don't involve geoboards, and here's one of them. Let's say we want to find the area of the yellow region. Now the yellow region is around a circle and it's inside a square. So if we think about finding the area of the square and then taking away the area of the circle, we'll have what remains, which is the yellow region we're looking for. So let's do that. Let's find the area of the square. And since the square is 20 centimeters by 20 centimeters, we'll have no trouble finding that area. To find the area of the circle, we need its radius. And the radius of that circle is half the distance across the square, which would be 10 centimeters. So the area of the square is going to be 400 square centimeters. And the area of the circle is going to be 100 pi square centimeters. So we've got the area of the yellow region, and we found that by subtracting the area of the circle from the area of the square. Now, just like before, if we really wanted to, we could do a substitution. We could substitute 3.14 for pi, and if we do that, we get an approximation of the area, which in this case is 86 square centimeters. How about if we want to find the area of this yellow region? So we're going to be able to do some subtraction to do this one as well, because the yellow region is inside a large circle, but outside these 2 small circles. So if we think about starting with the yellow circle, the big yellow circle, and then subtracting off the area of the 2 little blue circles, we'll have the area that we're looking for. So let's think about whether we know everything we need to find the areas. To find area of a circle, we need its radius, and we've certainly got the radius of the large circle. But do we have the radius of the small circles? Well, not directly, but indirectly we do. The diameter of each small circle is going to be that same 8 meters, but the radius of each small circle is going to be half of that, which is 4 meters. So now we can use our area formulas. We know that the area of the large circle is pi times its radius squared. And be careful with this one, we have 2 of those small circles, so we have to subtract 2 of the areas of the small circles. So we're subtracting 2 of the pi times 4 squared. Remember, 4 was the radius of the small circles. And we end up with 32 pi square centimeters of area that is in the yellow region. Once again, we can take that pi and we can substitute 3.14 for it to get a decimal approximation if we want a decimal approximation for this area. So that's our look at area of polygons and circles.